Welcome back, and let us resume our discussion on the offset cancellation circuit that we started with. Before we go further, any other questions in the discussion that we had? So, we looked into once again the negative feedback operation, how the amplifier is able to follow the signal at the positive terminal, and then we looked into the basic mechanism for the offset cancellation that we can apply to our comparator circuit. Now, let us go into the circuit issues that must be addressed to implement this operation in the comparator that we have designed for our ADC operation. For that, there are several issues that we need to look at. First of all, for the overall operation, we need to make sure that the DC bias point is intact. So, we need to see the DC bias point. We need to see the non-idealities of the switches. We have already discussed non-idealities of switches in significant detail. So, once again their implications have to be considered here, and we also need to look at the closed loop response. And finally, if I ultimately have to apply this operation on my circuit, I need to look at the input interfacing. What manner I am going to apply my input, which is coming either from the ramp circuit or the sampled analog voltage, to this offset cancelled amplifier or comparator. So, there are 4 things we can discuss step by step and look into the circuit issues related to these. So, first question I would like to discuss is the DC bias point. What is happening to the DC bias point of this amplifier when we are disconnecting the closed loop, then we are disconnecting this phi 1 switches. So, remember, for the phi 1 phase we have the overall operation, which can be given as a voltage follower. You have the VOS, and at this terminal you have a VCM, it may be VDD by 2, nominal value say VDD by 2, and as a result you are storing the VOS over here. So, if I look at the corresponding circuit implementation, what are we trying to do? So, let us try to implement this using transistor level circuit and try to see where are we going to place these switches. So, if I draw that on my transistor level circuit for the comparator, so this is our positive input, and we are connecting the first switch at the positive input, which is supposed to connect this to VDD by 2 say. So, we can have one transmission gate based switch that we have discussed in our previous classes, and this point can be VDD by 2. We can obtain it through some reference generation circuit or simply by dividers if we ignore the issues related to that right now. Now, here we have of course the phase phi 1 coming in, and also just to keep the track, we can enter that V offset over here. So, let this red dot be the V offset, the offset voltage that we have, and we also have the capacitor, which is supposed to be connected between the terminal over here. So, this is our C offset, which is once again supposed to be connected to the inverting terminal, while the inverting terminal is in the negative feedback configuration. This is also driven by phi 1 phase, and finally, the output once again should be connected to this point. So, you have another switch coming over here, which is also driven by phi 1 phase. So, these are the 3 switches driven by the phi 1 pulse, and then we also have the other 2 switches driven by the phi 2 pulse. So, this is what we have. You have the V I, V in plus and V in minus. And once again, if I recall my overall operation that we discussed for the offset cancellation, what is when we have the phi 1 phase open, this is the equivalent circuit, and we have a VDD by 2 point over here. So, this point is biased at VDD by 2, and as a result this point is going to be VDD by 2 plus V offset. So, if I assume that V offset is bad, around 50 millivolt of V offset is happening, then we have VDD by 2, sorry, say 0.9 plus 50 millivolt coming over here. So, still both of them are pretty close together in terms of DC, 100 millivolt and 950 millivolt. But in the next phase, when phi 1 is getting off and phi 2 is getting on, we said that this node becomes floating and it does not have any direct connection with any of the DC sources, and that is basically helping us in preserving the offset voltage across this capacitor, the C offset, that is preserving the charge trapped across this C offset. Now, of course, if we look at the input side, we are connecting the input to V in plus, and therefore, in the phi 2 phase, as I said, we are going to have the V in plus appearing at this particular input connected to the say positive terminal of this capacitor, and as a result, since we have trapped the charge across this C offset, the potential over here will be jumping to V in plus minus V offset, right. So, whenever we connect the phi 2 switches, this potential is V in plus, the phi 1 switch is turning off, as a result the potential over here must be equal to the V in plus the potential drop across the capacitor in this direction, and in this direction what is the potential drop across the capacitor? We have seen minus V offset, because this is plus minus in this direction. So, V in plus minus V offset appears over here, and therefore, as long as this is connected to V in, this will be V in minus that V offset, and if V in plus is having a certain DC level, therefore, this automatically is carrying that DC level plus the V offset minus the V offset quantity. The DC of course cannot pass through the capacitor, but because of the charge stored across the capacitor, it can always provide a step in the voltage. So, when you are connecting this positive terminal of the capacitor to V in plus, because of the charge locked in this capacitor, you are going to have this V in plus plus that Vc coming in series, and then you are going to automatically have the V in plus minus V offset coming as the DC potential here. And likewise, on the other gate, we anyway have V in minus, which is also having its own DC depending upon what is the signal level, whether it is V ramp or whether it is our sampled signal. It will have certain DC, this will have certain DC, and therefore, we are not going for any dedicated biasing circuitry for the input for the comparison phase. When the phi 2 is on, the amplifier is operating in the comparison mode. This is open, there is no feedback, and this is our normal comparator, the 2 inputs being applied to the gates of the comparator, and ultimately we have to just compare the absolute values, and we have to just make sure that the values are within the input common mode range of the comparator, as we have discussed. So, as long as the input voltage V in is within the input common mode range of this comparator, we are just concerned with the trip point when the Vref approaches this sampled V in, and under that condition anyway the DC bias point will be provided by the sampled V in over here and the ramping voltage over here. This is clear? Any question? So, this relates to the DC biasing. We are not biasing the input for any DC. Of course, we have discussed that in a comparator operation we need not be concerned about biasing the output also, because ultimately we are concerned with only high or low levels. So, for the differential amplifier operation in the front end, we have discussed the common mode feedback, and we have discussed a couple of strategies, stabilization techniques, but here we are not even considering the output DC point, and because the output will not be stable at one DC bias point, it is going to be nonlinear operation, either the output is supposed to be close to VDD or ground. So, where your input signal is sampled and this is at a certain value V sample and the ramping voltage is rising, this is your V ramp on the capacitor. We must make sure that in the vicinity of this time where you have the V ramp approaching Vs, the gain is sufficient and it is able to amplify the signal sufficiently. And under that condition, of course, if I assume that the transistors over here are remaining in saturation, we will still get a good gain. However, means we are not ensuring an appropriate DC bias point. We will discuss that a little later when we come back to the role of the DC bias point at the output of the comparator, that not only relates to the offset compensation, but also relates to in general the biasing of the single ended comparator and the resolution of the single ended comparator. So, we will get back to this point of biasing the output. What we are right now saying is that for the comparator output, we are mainly concerned with the output level going high or low. So, in this entire region the output will be high or low, VDD or ground. Therefore, we need not consider the saturation region operation and appropriate DC bias point for this one. All we want is as soon as V ramp approaches Vs, all the transistors should be in saturation, so that the decision regarding the transition should be taken at the right time step. It should go up, the transition should happen at the right time instance, that is going to give me the correct digital value. For that, I should make sure that the gain in this region is sufficient, so that whenever the difference, if I magnify this a little bit, so whenever the difference between the sample voltage and V ramp is changing the polarity, becoming from negative to positive, the comparator should be able to change the polarity within a very short time, and that would imply that at this particular juncture the gain of the amplifier should be sufficient, so that whenever there is a delta V, a small change in the polarity of V s minus V ref, the amplifier should be able to detect it and flip the polarity. And that is the only purpose. If you are far away from this region, here or here, definitely the output is close to VDD or ground. These are going to be in triode region, either this is going to be in triode region when the output is VDD, or this is going to be in triode region when the output is ground. So, for those regions we do not need to worry. However, we will see the case where even in this region, when the input is approaching, the V ramp is approaching the Vs and two are almost similar, even under that condition, of course, we cannot guarantee that this will be close to VDD by 2 and this to be in saturation. If they are not in saturation, suppose the output is very close to VDD, or it is remaining close to VDD even when these two signals are very close together. So, in that case, of course, it will so when the signal approaches over here, it will take longer time, and unless Vref becomes sufficiently larger than Vs, it will not be able to pull the output down, because to begin with the output was very close to VDD, and even when these two became almost similar, the output remained close to VDD. So, unless the Vref progresses sufficiently beyond Vs, it will not be able to pull it down. So, that effect is also captured in the form of offset voltage, that what is the minimum difference in the Vref and Vs required, so that the output flips. So, that effect is also indirectly getting captured in the offset voltage, if you consider this. Because what is offset voltage? Offset voltage is a point where if you are having the two inputs, if you are having the voltage follower configuration and you are seeing that the two inputs are almost at a similar point, or you are trying to see what is the minimum voltage that you can apply at the positive terminal, so that the output is close to say VDD by 2. So, that is what we are looking at, and therefore, that difference or that voltage has been anyway stored across the C offset. So, that is also having the effect of the uncertainty in the output stages captured in V offset. So, we need not worry about this at this point. What we are saying is this offset voltage is going to take care, this offset voltage stored across the C offset is going to take care of the not only the mismatch of the first stage, but also the deviation of the DC bias point over here when both the inputs are close together, because when both the inputs are close together, we need this V in plus this voltage drop to make sure that the output is VDD by 2. So, that is already stored, that is in fact capturing the effect of uncertainty in the output point. So, that is in a way ensuring that the amplifier will be in high gain condition when the Vref approaches the V ramp approaches Vs. That is another subtle point that you can think of. So, output DC point we need not worry about it in this case. Is it clear? Input DC point definitely we can based on the capacitor stored charge in the V in, we can say that okay, this is just going to have a jump, this is V in, this is going to be V in minus V offset. The moment you apply V in over here, this voltage is clamped across the capacitor, V in minus V offset plus V offset. Therefore, that is well settled. Also, what I am claiming is that the output DC point is also going to be well defined as V ramp equals to Vres, exactly equal to Vres, because at that point whatever mismatch effect was there, it is already being captured in this C offset. This is clear regarding the DC bias of the input point and the output point of the comparator. Of course, the other important issue that we need to take care of is the non-idealities of these switches. So, we are concerned with tracking the offset voltage and sampling it across this C offset, and the magnitudes can be maybe few millivolts all the way to few tens of millivolts, and we would like to preserve that accuracy, and the offset voltage stored across this C offset should not get corrupted because of the leakage to the switches. So, for example, when the phi 2 mode is active, we have the switch over here which is off, right, and you have the input signal applied to the C offset. So, in the phi 2 phase, what is the condition of this switch, this capacitor? You have the V offset stored over here, and you have the switch which is connecting this to input. So, V in plus is connected to the capacitor, and at the other side you have this switch driven by the phi 1 phase which is closed. So, here this can be shorted, we can say this is the phi 1 or the phi 2 phase where this input is connected to the positive plate of the capacitor. However, the phi 1 switch is off, and then you also have the gate of the MOSFET where it is connected. So, of course, we are going to implement these switches using transmission gates. Both these switches are going to be implemented using transmission gates, and we have seen that transmission gates do end up dumping unwanted charges at the sampling points. So, at this point, since it is a trapped node, we do not have any path for this charge to go. At this particular point, when the switch is getting on, anyway it is sampling the or passing the input voltage and is connecting this particular terminal to the input voltage. Therefore, even if it is injecting some charge over here, this is ultimately shorted to V in plus. It is connected from an effective source which is supplying that V in plus, which is maybe coming from previous stage or stored voltage in a capacitor. So, this is connected from a source, a stable source. Therefore, this switch after getting closed, if it is injecting some charge, it does not matter, because ultimately this is going to be sunk by this source effectively. However, this switch getting off, of course, that is going to inject charges on this point, and then once again we have the effect of clock feed through and charge injection coming into picture. And we must make sure that if I remember the bigger picture, you have these two transistors NMOS and PMOS implementing this switch, and I must make sure that the overall capacitances, the parasitic capacitances contributed by these transistors, they are much smaller as compared to the C offset. So, that the floating node over here does not experience inaccuracy, does not increase or decrease this voltage because of the dumped charges arising from clock feed through and charge injection from these switches. So, once again that would require certain sizing. So, remember the sizing consideration where we have the delta V because of clock feed through coming as CGD upon CGD plus C offset in this case times the delta V clock, we can call it say VDD, and we remember that we must make sure that the CGD is sufficiently small as compared to C offset. So, if this is few femtofarad, in order to preserve millivolt of accuracy, I would like this to be few picofarad. So, if you use minimum size transistor CMOS technology 180 nanometer, this can be close to 1 femtofarad. In that case, at least this would tell me that I should have at least say 100 femtofarad to few picofarad of capacitance for the offset capacitor. So, this is first concern, and of course, the second concern is stability of the offset voltage in presence of leakage. So, of course, we know that this is not a ideal switch. We have the leakage paths through this switch, and also you may have some gate leakage through this MOSFET, which is going to disturb the total charge stored over here. Ideally, if the total charge stored at this point remains clamped, then only we are having a faithful storage of offset voltage across this. But if that charge dissipates, it has path to dissipate, then of course, that stored voltage will diminish or change with time, and it will not give us correct subtraction from the applied input. So, once again this capacitor should be sufficiently large, so that the effect of leakage is small, and over the time when this phi 1 phi 2 phase is open, the voltage the charge stored across here is not getting dissipated because of the off resistance of the switches and the gate leakage, etc. So, once again we had done this analysis, we tried to see that for a given off resistance in the CMOS technology, how to estimate the C offset, and then again we had around at least a few picofarad of C offset coming into picture. So, once again assume that we are going to require around a picofarad of capacitor just to make sure that leakage is not disturbing this stored voltage, and we are able to preserve this for the entire duration of the processing. Now, of course, the duration of the processing or the duration of the refresh is going to be another important question before we determine what is the size of the capacitor. So, remember the operation that we have overall for the comparator. So, we have this sampling pulses T sample, which are possibly getting on periodically with the required sampling rate. We discussed the sampling frequency was around 250 kilohertz for 7-bit digitization. So, the clock that we are having, it is going to have at least 127 pulses between the two rising edges, that is going to give us 127 levels or 7-bit quantization. That was the design decision that we made in the beginning. Now, where can we apply this offset storage, where we can apply this phi 1 phase and the phi 2 phase? That is an important design decision. One possibility is that we apply the phi 1 phase aligned with Ts. So, we can use Ts for the phi 1 phase. So, during this Ts phase, when the comparator is not operating, I can use the phi 1 switches to store the offset voltage across the C offset, and in between we have the phi 2 phase. This is basically the phi 2 phase. So, in that case, the RC time constant once again is going to be similar to what we had for the sampling capacitor. So, for the sampling capacitor, whatever considerations we made, considering the off resistance of the switch and the overall leakage current through those switches, it is going to apply as it is here, because the overall leakage resistance or the leakage current is going to be similar in magnitude if I am using minimum size devices over here, and based on that we will again estimate that this C offset should be close to that sampling capacitor that we had with a few picofarad. And of course, if we add all other effects, the charge injection inaccuracy, the clock feed through inaccuracy, and then add up these non-idealities and estimate what is the value, it may be at least around picofarad value required for the C offset, which is close to the sampling capacitor. And the other option is of course that we can do it intermittently. We can use smaller capacitor, maybe 100 femtofarad, and we can do the refresh, the phi 1 operation intermittently. But that would require more complicated control on the digital part, and also in the analog part we will have to make sure that there is a there are certain regions, say within the clocking duration, where the comparator cannot be used. So, possibly when this clock for the counter is going down in one of these phases, we can use the offset sampling operation and turn the phi 2 switches, turn the phi 1 switches on, and again from the next rising edge of the clock we can again turn it off, and then we will have to make sure that the comparator output is only being used, say either in this positive phase of the clock or the downgoing edge of the clock. So, the timing control becomes more complicated if we are going for intermediate refreshing of the offset voltage across the C offset. We have to make sure that in between we break the normal comparison operation, we break the normal comparison operation and resort to offset sampling, and immediately after that, once the offset voltage has been sampled again reconnect the input to the 2 points. So, that would definitely we can see that we are going to have some more timing signals coming in. Rather than a simple clock, you need to have another timing signal which is going to tell you when to disconnect the offset loop and when to connect it back for the normal comparator operation. So, 1 picofarad, as I say, means here it is not a very serious limit, because we have seen the major capacitance is coming from the ramping circuitry, because for that circuitry, for robustness purposes, we have kept the current magnitude at least around 100 nanoampere or 0.1 microampere, and that gave us the maximum amount of capacitance around 10-20 picofarad. So, as compared to that, the overhead here will be relatively small. Therefore, if I look at the overall design, whatever we have as of now, this is not contributing a huge amount of area as compared to the bigger capacitor that we have. But if it is becoming very area critical and saving every micrometer square is important, then definitely we can go for options where you can minimize the areas because of these capacitors. And in those cases, only thing you need to do is you need to have a little bit more sophisticated digital control, which is going to help you in implementing the appropriate timing pulses. Any question related to this discussion? This is simple enough. We are just looking at the non-nullities of the switches and trying to recall our discussion that we had for the sampling switch. Any issues?
Sir?
Yes.
What about the effect of charge injection effect of the other switch?
As I said, the other switch over here, when it gets say open for the sampling the input voltage, there anyway it is connecting, when it is getting open it will be absorbing charge, and as a result of course, it will extract some charge from this point, but under that condition it is ultimately going to deploy the V in. The V in is going to be connected to this particular node, and therefore, during the turning on phase, even though it is extracting some charge to form its channel, both NMOS and PMOS of this gate, but you have a source over here which is supplying V in. So, ultimately this node will be charging to V in. When however, it is turning off, when this switch turns off, there also this node is not floating node, because in that phase if you see, you have this node connected to the feedback loop and going here. So, output over here is controlled by the output voltage of the amplifier. Only if it is a floating node, then that stored charge injected by the switches will be playing role. Whenever it is having connection to the other circuitry which are controlling that voltage, then of course, that additional charge will be taken care, it will be getting absorbed in the amplifier. So, both when it is getting on and off, it will not be causing trouble.
Sir, what is the problem if we do not switch off the VDD by 2?
Then what is the signal over here? Signal is VDD by 2, you do not have anything, this is DC potential, there is no signal.
Potential, then we have to give only signal, then it will be
no, then the charge across the capacitor is not constant, you have dissipated the charge. So, if it is floating, then only the charge is locked over here, and then you have the overall charge trapped and the voltage drop. If you connect it to VDD by 2, then the charge is gone. Okay, let us take a short break and then resume our discussion on the details of the circuit design.